We are on number 3. So it says Rufus swims the 25-yard freestyle with a mean time of 16.4 seconds. He decides to try an adjustment to his stroke, hoping to improve his time. So he records his time on 15 random swims using the adjusted stroke and finds the mean to be 16.0 seconds. At a 5% significance level, does the sample data support the claim that his mean swim time for all swims using the adjusted stroke is less than 16.4 seconds? All right, I repeated here the significance level. Assume swim times are normally distributed and that the population standard deviation is 0.8 seconds. All right, so let's start with writing our claim. So it's about the population mean. And he's wondering if by adjusting the stroke that his time for this event will be less than 16.4 seconds. All right, so we'll start there. So H naught, H1, colons. Our claim is that the mean for all swims using the adjusted stroke, so population mean, will be less than 16.4 seconds. All right, so we're dealing with a less than case, and that's what makes this a left tail test. Our null hypothesis is that the mean is 16.4, and then we'll go out and get some evidence to see if we are going to reject that in support of our alternative or not. So Rufus here goes out and gets some data. I'm going to put my mu naught over here first. So the mu naught is 16.4. And then he did an experiment using 15 of his random swims. And the sample mean for those 15 came out to be 16.0 seconds. Alpha, our significance level 5%. Go ahead and write that in decimal. And then we're to assume the population standard deviation, sigma, is 0.8. Okay, so this time what I'm going to do is just set up the traditional method, and then I'll come back to the test value. So for the traditional method, of course, we have our mu naught. And now, because it's a left tail test, the area left of our critical value will be alpha. So all of our alpha will be in the left tail, and we need that to be 0.05. So because that's the area to the left of the critical value, we can find that critical value z by using inverse norm, because we have the area left of z, 0.05. Okay, so let's enter that. So we'll inverse norm the area left, so alpha, 0.05. And it is coming up negative. That makes sense. As a z-score, we should be left of center, so the negative side. And then this is the value that if we rounded it to 2 decimal places, it would be negative 1.64. But in our textbook, we use negative 1.65. So the results of this test at the end will be the same, whether we use negative 1.65 or negative 1.64. And it really doesn't matter which one you put, even on Alex. But when we do 2 decimal places, this is the one that our textbook uses. So I'm going to stick with that as we've done in the past. All right, so let me draw our critical value on our graph. So negative 1.65, maybe about there, critical value. So this is the opposite of the z-score that would be on the right. So this is the negation of z alpha. So this notation you'll see on Alex, but you do not need to use it in class. We can just say critical value. So that's the location there. And then the critical value is that z-score that places an area of alpha to the left because it's a left tail test. So this area to the left is 5%. And the z-scores in that shaded area are in the critical region, also called the rejection region. So values that are not part of that shaded area in terms of z-scores are not in the critical region or the non-critical region. And that's our setup for traditional method. All right, so we have to take care of that ourselves. But now in order to find the test value, we can get the help of technology. And because we're doing a hypothesis test of a mean and sigma is known, we can use our z-test. So because sigma's known, excuse me, because sigma is known, we use a z-test. We're going to be switching to a t-test shortly, but for now we know sigma. So we'll go to our calculator to find our test value. So we'll go to our tests and our z-test, enter our mu naught and our sigma 0.8, x bar, sample mean 16, sample size 15. And for the direction of the test, so it's a left tail test. So mu smaller than, remember that value is mu naught. That value is mu naught. So we want mu less than. So make sure you pick less than there. And then calculate. We'll round that z-score to 2 decimal places, negative 1.94. Okay, and now we're ready to continue with the traditional method. All right, traditional method says graph your test value and see where that's located. So even if you don't have the graph drawn for you, you'll want to just make a sketch on your own when you're doing problems and label the information so you can figure out where your test value falls. So in this case, this is negative 1.65. It's a little bit of a crowded picture there, but right there is our test value, negative 1.94. So that value tells you that x bar, so this is telling us where x bar is relative to the critical region. So on my x bar axis, that's where 16.0 would be. So it's falling in this shaded critical region part of the graph. So my test value falls in the critical region. And when that happens, it means that that's a significantly low value relative to 16.4. So we say that's a significant finding. It's in the critical region. And that means we're going to be rejecting the null hypothesis in favor of the alternative. All right, so I'm just going to add this at the top. So no matter what method I use, we should get the same result. The traditional method said we're going to reject the null, and that would mean that we support our claim here because that's our H1. So it does seem that there is evidence to support the claim that the adjustment is working to reduce his time. All right, so I didn't write the sentence yet. We'll do that at the bottom, of course, but let's switch and do the same problem using the p-value method. So p-value method's always a little easier. You don't worry about critical regions. The only thing you graph is your test value. So let's put in our test value here. Now we've got a little more room. Test value is negative 1.9. All right, so that tells us 16.0 as X bar would be there. And that is our test value. And now because it's a left tail test, the area left of the test value is called our p-value. So that area is our p-value. So I keep these pictures separate so you don't confuse the methods, but that part that I just shaded up here would be the part beyond my 16. So that p-value area is smaller than my alpha area. So I can see that visually that my p-value is smaller than my alpha. Technically, we say less than or equal to, but it will be actually less. And then we can confirm that on the calculator. It says our p-value is 0.0264. And I could stay in decimal to compare to alpha. I just like to write it as a percent. And then I'm going to confirm that my visual was right. So if p is 2.64%, and then alpha was 5%, my numerical values match my visual. That is smaller than that. So again, it is technically less for sure, but we just say less than or equal to. All right, and then the little rhyme is that when your p-value is low, you let the null go. So when our p-value is lower than alpha, we let the null go. So the decision again, we let the null go, we reject H naught. So of course, the decision on the traditional method and the decision on the p-value method will always match because we're doing the same problem in two different ways, which means that anytime your test value is in your critical region, it guarantees that your p-value is small. And then in both cases, the sentence would be the same. So based on a sample of, and this was 15 swims, we conclude that there is enough evidence to support the claim that his mean swim time using the adjusted stroke is less than 16. So just going again up to our claim that the mean is less than 16.4 seconds. All right. So there's the example of a left tail test.